17 hours in the air to get here, but it's a great feeling to finally be here. I've heard so many good things about this conference, and it is a real pleasure to present for you today. What this talk is about is looking at finding 0 days and writing exploits for embedded devices, and really our approach that we use at InfoSec to find 0 days and write exploits. So it's some case studies of embedded devices, mostly focusing on routers, Soho-style routers, but the same approach works on many types of embedded devices, including security cameras, NBRs, all those types of things, smart home assistants and so forth. We're going to talk about firmware analysis, so downloading firmware, looking at firmware, extracting firmware to get software, understanding what attack surface you have exposed on a particular sort of set of devices, whether it's a router, a NAS, security camera, an NBR, and so forth. Once you've got that software and you understand what you're sort of looking for, you want to actually find some bugs, so a bit of vulnerability research, decompiling software, static analysis, fuzz testing, and so forth. To write an exploit, it's often easier to work on an emulated environment as opposed to working on the real hardware to start off with. You want to migrate to the real hardware eventually, but it's much easier to do your exploit development in some sort of emulated environment. So I'll talk about that, and then I'll talk about writing exploits, the type of approaches that you would use to write exploits against a typical IoT device or an embedded device, and then I'll conclude the presentation. To give some context, what this sort of looks like as sort of an end result, I'll look at one of the phone-to-own targets in 2020, late 2020, an embedded Soho router. This particular device that I'm looking at, the threat model is that you're on the network, the Wi-Fi network perhaps, maybe you've used a Wi-Fi Pineapple or something like that, or you're connected to a network port in an office or something like that. But what you really want is administrator root level access to that router. And this is a 0-day exploit that we wrote against this phone-to-own target. Often we'll ask the question, can we, when phone-to-own devices are released as targets, can we write an exploit? Can we find some 0-day bugs against these devices? And for this one, we were able to. So this is a Netgear Nighthawk router. It's still shrink wrapped, so it's we just ordered it brand new. I'm on the network. Wi-Fi's typical sort of access you would have. This is a LAN side exploit, so there are WAN side exploits as well where you're over the internet, but I'm on the network. I run the exploit, and it immediately opens up a bind shell listening on port 9999. I telnet to it, and I'm running as root. And then, just for show, I'll turn on the LEDs of the router. So very quick to work. It's only throwing 1 or 2 packets to the device and getting remote code execution. So the rest of this talk is going to be how that approach works. How do you actually find those types of 0-day bugs? How do you write exploits for these types of devices? And it all really starts with firmware analysis. There are different approaches that you can use to get the firmware off an embedded device. Maybe you can intercept web traffic through a proxy like pfSense and capture plain text HTTP web requests and pull out a download link and download the firmware. Maybe you have to physically interface with the device. Maybe you have to attach some test clips, desolder some NAND chips or something like that and pull off firmware that way. The easiest approach, and this works especially for routers, is just go to the vendor website and download the firmware. That's sort of your best case scenario, that you can just download the firmware. The worst case scenario, if it's encrypted, and it's encrypted on the flash, and so even if you desolder it, it's still encrypted, so there's other ways you can get around that. But in this particular case, this Netgear Nighthawk router, we can just download the firmware off the internet from the vendor website. The firmware for this particular router is just in a zip file, and you can just sort of download from the URL, from the vendor link, and pull this complete firmware, including the root file system, off this router. Once you've got that download image, I suppose, sort of a zip file, you want to unzip it and then look at the image file, and a common tool that you would use to pull out the root file system from that firmware is binwalk. Binwalk with the -e to extract option. The image file is as an argument, and we do this on this particular firmware image that we pulled off the internet, and we can see right at the end, it's pretty small writing, so you're not expected to be able to read all this, but I can tell you at sort of the end of this output, there's a squash file system that's been detected, and the root file system of that router has been extracted from binwalk. And if we look at what we extracted, we can get all the files of the image. We can see the root file system, etc, bin, sbin, user, all of those directories that we typically expect on a root file system of an embedded device. SquashFS is a very typical file system implementation that is used, and there's a bunch of tools to extract that. Binwalk supports them already. Sometimes firmware might be use modifications of those common file system formats, but you can get around that, and Binwalk is a great tool to look at these particular images. You want to look around this file system image, see what's there. A lot of people don't know this, but some of the Netgear Nighthawk routers actually have this binary called AWS IoT. It's actually a service that runs via cron once a day on your Netgear Nighthawk router, and it connects over the internet to these IP addresses that are hard-coded into these binaries over Amazon AWS, and sends statistics about the router to the vendor. So they'll send information about the current load average on your system, process listings and so forth. And you might not even realise that this is happening, but maybe your router is doing this underneath the hood. And there's hard-coded private keys, presumably to connect to those trusted Amazon EC2 images that are out there. You've got a file system image. You want to do your typical sort of pen testing style approaches. Look for backdoor accounts, standard security checks, etc password, etc shadow. A lot of embedded devices will have backdoor accounts, and sometimes there might be authentication if you get serial console access to it. So if you've got the firmware, you might be able to sort of crack the password or get a bit more information about it. Maybe there's cryptographic keys as well. These are all things that you want to look for when you've got that file system image, and very easy in this particular case that we just downloaded the firmware. On this particular device, this is a Unify. Again, you don't have to read this. I'll explain all the content on these compressed slides. But this is a Unify Wi-Fi access universal dream machine device. This is the sort of Ubiquity series of devices that are out there. And this is the default firmware. And if you look at the etc shadow file, which includes passwords or hash passwords and usernames and so forth, we can actually see that there's a hashed password in here for the root account, and it's just Unify. It's a default password that you have on first install. This is okay for this Unify device because after you install it, you have to change the password. But if you just, if all devices aren't like this, they might not force you to change that password on first login, and there is a default password that you need to sort of log into the device before you do that. Once you've got the file system image and the root file system as well, you probably want to look at the etc and netd files. These are all the startup files that sort of initialize or start on boot up. Init tab, RCS is sort of your standard thing that you look at. Anything in this netd directory are the programs or services that get started when the device boots. They're not always default on boot. They need to be enabled sometimes, but there is a sort of a default set that you probably want to look at if you have if you're looking for a 0-day or an exploit in default services. Another good option, if you actually have serial console access to the device on a running system, just run netstat, see what services are listening on TCP and UDP ports, see which processes they're attached to, and those are the things that you want to audit. This is really sort of the goal of this is to know what to audit for. You've got the firmware. It's a big sort of set of files. What are particular services that have bugs that if you find something useful in, you can get some sort of remote code execution in some sort of default configuration. This is where you want to focus your time. And in this particular device, this Netgear Nighthawk XR500, it has a bunch of services in the initd directory. Not all of these are going to be enabled on startup, but you want to look at that RCS file as sort of your default thing that runs on boot up. But you can see Samba, AFPD, a bunch of other things. All of these are very useful things to audit. So we've got a sort of a concept now that we've got the firmware. We have sort of an inkling of what things we want to audit for. So that's a pretty good basis to start our sort of our vulnerability research process and start our quest of finding some sort of remote code execution or something like that. But really, we can also take a step back and start to sort of see patterns in sort of general classes of devices. A lot of routers, for example, will have very similar services that they run. Most NASs will have a sort of a similar construct as well, and they'll have a sort of a standard attack surface. Security cameras have a sort of a standard design pattern as well, or NVRs have standard design. So if we understand the category of device that we're looking at, we have a much better idea of where to focus our time in the vulnerability research process. Most IoT devices that we look at least, are going to be Linux-based. It's a very universal operating system that gets used for embedded devices. Typically, the Linux kernel version that they're running is going to be much older than mainline. It's just a standard practice for IoT devices and embedded devices that they're running older Linux. This is sometimes useful if you have some sort of application whitelisting or secure boot process and you want to sort of privesc and avoid all of those things. An end day in a kernel is probably going to be useful. Most IoT devices and embedded devices do have some sort of management interface or management portal, I suppose. So a lot of them do have web interfaces. Routers are a very common example of this. You go to sort of the router page that your device has, and you can set configuration options, set passwords, usernames, configure different services and so forth. Most IoT devices are running a web server, and if they're not running just a web server portal, they're using some sort of web server infrastructure to do RPC mechanisms to enable services or do certain things on the network. Generally, if it is using some sort of web server portal, it's probably some variant of a web server that you already know. So UHTTPD, Lighty is another one, micro HTTPD. All of these things are sort of customized for this particular device. So most of the time they don't write a web server from scratch. They take some sort of off-the-shelf web server and then customize it for their situation. So learning those different web servers and how they're coded is a very good thing to spend your time on. CGI handlers are very common in embedded devices. This is sort of just the way it's done to sort of interact with the operating system or these devices by sending CGI requests. And often these CGI requests are a good attack surface to send untrusted input, create buffer overflows, memory corruption, and all of those types of things. A lot of devices as well today will have some sort of USB port associated with them. Maybe it's to do a firmware upgrade, maybe it's for removable media or something like that. It does open the attack surface to say, well, you've got you can put a USB stick, so you're touching file systems, you're touching USB drivers and so forth. In practice, a very useful thing for USB and removable media is just copying files back and forth across from yourself to the embedded device. So if you want to pull the file system off the embedded device, you'll get serial console access to it and then copy it to USB stick. Or if you want to copy your tool chains that you're doing exploit development on or VR processes or debugging, you'll put them on USB stick and then copy them onto the embedded device. If you don't have USB, you can just use TFTP or some other sort of approach, but USB is a really good option. The TCP/IP stack is almost always exposed. They're IoT devices, embedded devices, they're network connected generally. Generally, not always the case, and I think there's another talk this week where this isn't the case, but generally the network stack isn't your first go-to attack vector on a device. Sometimes firewall configurations might be weak. You might be able to turn a LAN side bug into a sort of a WAN side internet sort of connected bug if there's some sort of weak firewall configuration. But in general, specific network services running on the device are generally the thing that you're going after. Those are the things that have most likely sort of the easier to exploit bugs that you can find a 0-day and get code execution on. Now, for general IoT, DHCP is pretty standard networking protocol. Most devices need to be able to dynamically obtain an IP address on the network, and so IoT devices have a DHCP client. This is good attack surface. If your IoT device is, say, a router or an NVR or something like that, it probably also has a DHCP server, and that's a very good attack surface as well. There's often standard tools and services like DNS mask, UDHCP, C and D. These are very common upstream softwares that are generally modified or customized for that specific device, that specific embedded device where the vendor wants to add their own features. Universal plug and play is sometimes common in embedded devices. You see it on routers quite commonly. And of particular interest, a lot of vendors are now going towards their own custom zero configuration networking protocols as well. So the idea of this is if you have a vendor and you've got one of their devices, or maybe you've got 5 of their devices on your network. You want to go to your mobile phone app and say, what are all my TP-Link devices on my network? And there's often these zero configuration style networking services that broadcast across the network, detect other devices by the same vendor, and report all of this information. There's also classic zero configuration networking like MDNS, where you don't have, all of these things are supported by most embedded devices. And so you don't have to have a DHCP server or a DNS server on your network if it uses something like MDNS. Avahi is a common upstream provider of this service used to implement these features. Now, most IT devices, not all IT devices, but most IT devices run all their network services as root. So if you get a security camera off your local consumer electronics store, probably all of those services running on that device are running as root the network services. And so if you exploit a network service in one of these devices, you're probably going to get root access to begin with. A lot of IT devices don't also use secure boot or application whitelisting, so generally once you've got code execution, it's pretty easy to move around the system and do stuff. Some devices do have secure boot, and there's not all vendors are going to be the same, and there's you might need some additional steps, but a lot of IT devices in the consumer space, at least in the SOHO space, at least don't use those types of mitigations or controls. A lot of IT devices, so your home router, for example, probably doesn't use stack canaries for most of the network services that are compiled on it. They're probably not using Relro or using the full capabilities of address space layout randomization. They're probably using a variant of libc that doesn't have much heap hardening, so heap exploitation is easier as well. And that's just standard across the board. And I think one of the reasons for this is that the common tools that we use to build embedded systems, the default configuration is that these mitigations aren't enabled. I think once upstream enables these mitigations, vendors will just do the default install, and then they'll magically get more secure overnight. Like I said, most IT devices are probably using UClibc or something like that. They don't use glibc typically. They don't have strong heap hardening, so old school heap attacks. You don't have to use much modern stuff. Most of the old school heap attacks will work. Even a lot of devices out there are still running on MIPS, so routers are a good example of this again. It's not all just ARM out there. MIPS is still very common. Only in recent past couple of years, recent Linux kernels have they had non-executable stack and data in the MIPS Linux kernel. So in practice, if you have a MIPS device on your network, probably doesn't have DEP enabled or DEP possible because the kernel doesn't support it, because it's running an older kernel that doesn't have that type of mitigation in it. Modems and routers are common IT devices in home networks. SOHO routers are very common. Modems are often combined with router functionality, so your Wi-Fi routers, the gateway, it's all merged together. In practice, the more expensive your SOHO router, the more feature-rich the device is, the more likely it is to be exploitable because you just have a bigger attack surface. Attack surface, there's generally going to be some sort of web server or web management, so there's a web server running. And they'll probably use some sort of DHCP server based on UDHCPD. They'll often have Samba or other network file systems. Sometimes they'll have FTP access, more attack surface. Sometimes they'll have media streaming or downloading functionality. And they'll probably support universal plug and play as well. So all of these things are good attack surface to work with. The typical types of bugs, this is, you don't have to read this, I'll just explain it to you, but these are sample CVEs that are in the public domain. This is a stack-based buffer overflow in a web server, and you get code execution. So really old school bugs work on these types of devices. This is the Netgear Nighthawk router. There's quite a few variants of Netgear Nighthawk routers. This is one variant of it. The DHCP service, you can get an XSS by having a host name of your device that's registering across DHCP. Universal plug and play, a stack-based buffer overflow. Generally, stack-based buffer overflows are pretty good. They're pretty reasonably mitigated on modern desktops, but on embedded devices, they're probably going to be exploitable. NAS is another good class of devices, set of devices to look at. They'll probably have some sort of web management interface. It's very standard. Typical vendors are QNAP, Synology, Western Digital, and so forth. They'll have DHCP clients, media streaming downloaders, customized web servers. CGI functionality is pretty standard to interoperate with these things or integrate with these things. They'll have customized FTP implementations, Samba, customized NFS, all really good attack surface to find 0 days in. Here's a sort of a bug in QNAP, which is pretty common. NAS. This is just a command execution bug in sort of one of the CGI functionalities in one of the modules that they run. Command injections are super common in embedded devices. This is really probably the first thing that you want to audit for. Why bother about memory corruption when you can get a command injection? But memory corruption is easier on these devices than desktop, so it's pretty good. It's a pretty good thing as well. So we sort of know now that, what sort of we're working with. We've got the firmware. We know that these network services are sort of interesting targets sort of to look at. We have an idea of the attack surface of some of the devices that we talked about, so SOHO routers, we briefly mentioned about NASs, but the same is true for other devices as well. You just have to learn your category of device that you're working with for how they're sort of implemented in practice. So, now we want to find some bugs. We've got some things to audit. We've got some binaries. We might even have source on occasion, but we want to find some bugs. The main approach is to find bugs that are, that we're going to exploit. Code review, so reading the code or reverse engineering the code. Fuzz testing, so using some automated testing. There's a lot of harnessing involved required to sort of get your network service to be fuzzable. That's sort of the craft of fuzzing, I suppose. And there's also static analysis, so some tools that will analyze our binaries or our source code to find bugs as well. Sometimes we have the source code. That's good. That's sort of the easier approach. But if not, we've got binaries as well from the firmware that we pulled off the device or downloaded or whatever we have. This was another router in the Pwn to Own 2020. This is a TP-Link AC1750 smart Wi-Fi router. A lot of routers, as you spend more money on them, they get more sort of exotic in looking in shape, and they end up looking like spaceships by once you start paying sort of the top end money for it. But this is a pretty standard looking, conservative router, I suppose. Now, TP-Link routers do have a zero configuration network management capability. Like I said, you want to go onto your mobile phone app and you want to say, well, what are all my TP-Link devices in my TP-Link cloud at home? And the way that these devices implement this feature is by having extra network services that run on these devices. So TP-Link routers have this service present in them. We can acquire the firmware for this particular target router, which is the TP-Link TC-AC750, and we can analyze the network services or daemons that implement these services. And for this particular service, the source code it's closed source because it's not based off any existing upstream implementations. It's TP-Link's very proprietary implementation of their zero configuration networking management tool or whatever it is. And the daemons run as native executables. They're originally written in C, as most things are in embedded devices, at least at this level. The binary is called TDDP. It's TP-Link Device Discovery Protocol. And pretty standard, you just pull it in Ghidra, decompile it, and start reversing it to try to find some bugs. Obviously, the source code from Ghidra is good, but not as good as you would have if you had the original source code. And what I wanted to do, and what I did, was I looked at all parts of the network protocol that were pre-authentication. So there's an authentication process that goes on with these devices, but there's a set of commands that you can sort of request of these sort of devices or on this router from this service that is pre-authentication. So you can get different types of information from it. And it's a very simple protocol. It's basically, again, you don't have to read this. I'll explain what it is. And in fact, even if you could read this, you're not expected to read line by line here. I'll explain what it is. But the way this protocol works is you send a request with some sort of command request, and then it responds. And some of these commands need authentication, and some of the commands don't need authentication. But if we look at this disassembled output, or decompiled output rather, we can actually see that there's a bit of error message printing, printf, and it says tddp exec command, and then there's an exec-v of binsh later on down below. And what this is just a re-implementation of the system library call. It will execute a shell command that is passed to it as an argument. And they just added some extra sort of instrumentation to do some debugging around that. But it's basically an implementation of system which basically executes shell commands that are passed to this function. Now, if we look at the main part of our service, which is sort of the request handling and looks at the command that's being requested of it, processes it, sends back a response, One of these commands, and a few of them are pre-authentication, but one command in particular that is pre-authentication is the command ftest config function. And I know that's what the command sort of is because there's debugging information around it that says this is what this particular request is. And if we look at this code in a little bit more detail and we see what actually implements this request or this handler, there's actually a bit of code at the bottom that calls TFTP with an argument that's passed to it from this command request, and it uses our system implementation, re-implementation of system to execute this shell command. And what we have here is the ability to pass untrusted input into a shell command that's passed to system. And that's pretty much your classic command injection sort of vulnerability. So very easy way to send untrusted input from a device on the network to the router, and the router will just execute this TFT command, pull some sort of configuration file, but we injected a shell command by using shell meta characters like semicolon or backticks or $signs and so forth. And under emulation, this is how I sort of tested this bug initially. I didn't run it on the real device. I emulated it to sort of see if this exploit would work. And it's entirely legitimate and works as expected. I can execute arbitrary commands from an unauthenticated user on the LAN. But there's some problems. This service is only started when factory mode is enabled on the router. And that seems to be after a sort of a reset or when the device is sort of fairly new. And so this is a bug that's, it's a good bug if it was a default configuration, but it's not a default configuration, so ultimately it's not that useful at all. And it's actually more interesting than that. It's not even, it turns out that this bug isn't even a 0-day. So I found this bug by auditing this team, and I thought, oh, I've got a pretty good bug here. And then I started Googling to see if anyone else knew about this protocol or this zero configuration networking. And it seems that someone wrote a blog post about this exact bug on another router, the SR20 router by TP-Link. And in this particular blog post, they talked about that the TP-Link had fixed 20 of these routers that had this bug, but they clearly didn't know that this particular router, this point-to-own target router, had exactly the same bug, except it wasn't enabled in the default configuration. So not a 0-day, but maybe TP-Link, and generally that's a very common practice that the development practice of these IT vendors tends to be really ad hoc, and they'll backport stuff between different trees, and it's really chaotic. And I would say it's very difficult to know without sort of larger scale analysis if one bug that you have in one device applies to which routers, because a lot of these bugs are shared across devices. But there's another bug, it seems. There's a developer backdoor in this initialization. So this particular initialization tries to TFTP a file from this IP address, a hard-coded IP address. It's called autocal2g.sh. It's actually a shell script. And I don't show you executing the shell script here, but when it downloads it and it's present on this hard-coded IP address, it will just execute it. So that's probably not a good idea for a production device to have that. But it's okay. The developer backdoor is only enabled when the TP-Link device discovery protocol is enabled, so it's not a default configuration, so it's not really a major problem. And having these sort of constraints on a 0-day that you have to have some sort of configuration enabled is not really a good position to be in, and you certainly wouldn't be able to compete in point-to-own with these types of bugs. And really the solution is just to look for better bugs, look for more network services, look deeper in the network services that you have available to you. And there are better bugs in most of these devices most of the time. So, okay, so let's just assume, and I'll talk about some more successful 0 days later on, but let's just assume that we found some useful bugs from our vulnerability research process. We've audited some network services, we've done some reverse engineering, we've done some code review, we maybe did a little bit of fuzz testing, we got some bugs, and we want to write an exploit now. And really, I would say the easiest approach for most IT devices is to emulate the network services and develop your exploit around that emulated environment. You don't always have the ability to do that. Some embedded devices do have sort of exotic hardware that is hard to emulate. There are other approaches to work with that. Maybe snapshot fuzzing or something like that is an approach. But really, if you can emulate it, you're going to be much better off, and you'll probably be able to fuzz it as well, which is probably going to support you finding more bugs. The assumption is that you've acquired the firmware, whether from physically interfacing, desoldering chips, doing chip off, or downloading the firmware image, or intercepting web traffic, or dumping from the bootloader, or whatever it might be. And you pulled out the file system of the IT device, the root file system, and you've got access to all the network services that are in there, and it's going to be Linux-based. That's our assumption. That's not always true, of course, but for a lot of devices that you will see in sort of this consumer electronics, even enterprise, of course, will have Linux-based systems. And that's what we're focusing on in this talk. Generally, you just want to find out what architecture it's running so that you can emulate it appropriately and write your exploit appropriately. ARM is very common. MIPS is also very common, even though it's a little bit older. x86 is out there on some devices as well. And for ARM and MIPS, there's different variants of these architectures that you have to know before you emulate it appropriately. You can use the file command to see a little bit of information about an executable on that root file system that you've extracted. Or you can run readelf with the -A for all option, or the -A to show you architecture information as well on a particular binary and executable in that root file system. And so here we've got this XR500, Netgear Nighthawk XR500 router, and we've just run file on user sbin UHTTBD, which is the web server that's running on it, and it says to us it's an ARM binary, and that's a pretty good, we pretty much know the architecture from this. We can run readelf as well, which gives us sort of similar information. We learn a little bit of information about the architecture, and we'll also confirm that once we start to emulate it and try to emulate some simple binaries like binls or something like that, we'll see if we've appropriately determined the architecture and our emulation works correctly. QEMU, or Quick Emulator, can emulate a variety of architectures, including ARM, MIPS, x86, and so forth. QEMU can emulate a whole system. It can boot an operating system from a disk or a RAM image or something like that, or it can emulate user mode applications using the host operating system kernel to emulate, to run those real system calls. For quick testing, this user mode emulation is the way to go and is a good start. But once you've done that user mode emulation and you've got that working, to do sort of exploit development, you probably want to transition into whole system emulation. You have a much better opportunity to use native tool chains without all this emulated things that you have to sort of proxy in between. There's a couple of ways you can do user mode emulation in QEMU. You can basically just go into the root file system that you've extracted of your firmware of your device, use the -L option to say that my library path starts here, and then run your binary, and it should be able to emulate it. Otherwise, you might be able to chroot into that file system image or file system directory tree that you've pulled out, and then execute your emulator, and then run a shell to emulate that shell or whatever binary you're executing. Again, just to sort of reiterate, the -L option specifies the library path you use so that when your binary that you're emulating, say binls, uses uclibc, it knows how to load that library correctly. So that's why you need to use that -L option. Most binaries on these systems, well, to start with, that we're looking at are going to be dynamically linked, but there's obviously statically linked ones as well that don't need this option. And we run QEMU ARM with the -L option of just the current directory in our squashfs root. And we run binls, and we're able to emulate that binary. So we can emulate a simple firmware binary using QEMU ARM. That's a pretty good position to be in. That's going to help our exploit development. But we'll probably want to transition into whole system emulation soon so that we can use our our bigger tool chains and bigger development kits with that. Another option, sometimes you might want to do this if the network service that you're using makes references into the file system so that the root file system is in its correct place. And you basically copy a static version of QEMU into the firmware's root file system, chroot into that root file system, and execute the emulator with the target program of binsh or whatever network service you're running. And now you've got an emulated binary that you're running. And we can do that here. We've copied QEMU ARM static. That's just a package that is part of a package that we installed on Linux. We chroot into the current directory, which is our squashfs root that we extracted. We'll call our emulator, our statically compiled emulator, and then we've just executed binsh from our squashfs root, our file system, and we're able to emulate that quite easily. Now, this is sort of a good place to be, but you really want to do whole system emulation, I think. If you're fuzzing, you might not want to do this. Maybe you want to stick to user mode emulation. There's different pros and cons to different things here. But for exploit development, whole system emulation is probably the way to go. You need to have a disk image for us, a QCOW file is sort of called in QEMU. You need to start QEMU with the right architecture. Probably want to set up port forwarding so you can SSH into your guest and interact with your emulated environment. And there's some good sort of resources online. There's some, this person from Debian has made a bunch of QCOW images and kernel images provided that you can just download off the internet, and immediately start emulating an ARM Linux system or a MIPS Linux system without really much work at all. You start QEMU system, not that QEMU user application anymore. And if you're able to do that, you can emulate ARM, you can emulate MIPS and run a Linux system that boots up just like a normal Linux system, but running whatever architecture you're emulating. And it looks just like a normal Linux system. We've got a GUI here. You don't always need a GUI, but it's nice to sort of look at. You don't need to read that. It's just Linux booting in this particular image, which is ARM or MIPS or whatever it might be. And we can SSH into this guest, and now we've got an ARM guest that we're able to run ARM binaries on. All we really need to do is copy our firmware across chroot into it, and we're able to emulate a network service. And that's all we do. We SCP the firmware image. We've got that SSH forwarding to our guest, untar that file system root. We chroot into that file system, and we run binsh, and now we've got sort of a shell that's running in our ARM emulated environment. And this is a really good place to be now. We're able to emulate a network service. We're able to emulate a shell. We found a bug through our vulnerability research process. Now we want to write an exploit. And I'll talk about one particular exploit that I wrote, or one particular 0-day that I wrote for a router, a common router. And the background for this is that through manual code review and sort of the vulnerability research process, I discovered a pre-authentication stack-based buffer overflow in the web server implementation. The attack only requires one single HTTP GET request, and this web server is enabled by default on the LAN side of the router, but can be enabled on the WAN side as well. If you go to Showdown or whatever it might be and start looking for these routers on the internet, you'll probably find open ones. Sometimes internet service providers badly enable some sort of, some of these web servers on the routers they give to customers. Now, generally, the first step in the exploit development process is to trigger the bug and cause a crash, just to sort of put your mind at ease. Yes, it's a bug. I definitely found something. I'm not imagining it here. The way that I did this, which is sort of a dubious way, was, I suppose, I just compiled the router source code. I had that available to me. I compiled it with debug symbols, and then I tried to sort of trigger a crash, and I was able to do source code sort of debugging, source level debugging on it, and make it much easier to work with. The main result I got from this was that you needed a referrer header as part of the web request to trigger the appropriate code path, and you also needed to add a timestamp as part of a sort of a web request. And this timestamp needed to be within a couple of minutes of the web server's real time. And this seems sort of, maybe this is annoying, but it's actually a really good thing, because it means that fuzzing probably isn't going to be able to find this type of bug, or at least not reliably reproduce the crash. And so this is one thing that manual code review is probably going to be more fruitful. It'll probably be a longer living bug than if it was found by fuzzing. Now on x86, the buffer overflow cleanly overwrites the return address of the function on the stack. This is my compiled version that I was just using for testing, and it allows control flow to be hijacked. So that's pretty good. I mean, it's a pretty good position to be in. The next step I wanted to do was emulate the real web server firmware under QEMU. The target architecture is ARM. The firmware binary use DEP, so data execution prevention. You have to basically ROP if you're getting sort of memory corruption here, or do data-only attacks, or whatever it might be. And it does use ASLR. The binary isn't Pi, so the application code and data isn't using address-space layout randomization, so we might have a lot of fixed gadgets that we can ROP into, which is a good thing for exploit development. Now, in an ideal world, for ARM, I would just overwrite the return address on the stack with the gadget to move the stack pointer into the argument register and then ROP into the system library call that is almost certainly available on this particular binary. Most of these network services have system available to them because they use them for IPC mechanisms, in a pseudo sort of way. And that would allow you to execute arbitrary shell commands. And then what you would do, you normally start a telnet service running on a high port with a binsh as the login, and then you just telnet into it and you've got a root shell. Now the text segment for these gadgets contain a null byte. So the code and data of the application, even though it's non-pi, does contain null bytes. And this is problematic because we can't build a ROP chain because we need multiple null bytes in our addresses for this buffer overflow, and it's a string-based buffer overflow attack. So this is problematic. And there's even more problems. On x86, it was a clean return address stack overwrite. Now, on the real target, the web server crashes before it overwrites a return address. And what's happening is that there's an application pointer on the stack before the return address that points to a JSON object, and this JSON object is passed. And because we've corrupted the stack, this application pointer is corrupt, and now it's pointing to an invalid JSON object, and we're getting sort of a crash before that. So that's a real problem out. Your classic OSCP style, overwrite the return address doesn't really work in this particular case. Now, because the web server isn't pi, the text and data are at fixed addresses, and you can actually sort of make some HTTP headers with the user agent and so forth, point to these fixed addresses in memory. And so we can actually put data into sort of the address space that we control using this. And what we're going to do is corrupt that application pointer with a pointer to a fake JSON object that we're going to sort of smuggle into our user agent and build it that way. And we'll modify our exploit to overwrite that application pointer pointing to our fake JSON object, and hopefully we can make some progress and not crash our program. And it turns out this is even better. This fake JSON object also stores a kind of virtual function table or vtable, and we can hijack control flow not by overriding the return address on the stack, but by making a fake function pointer in our JSON object that is in a user agent part of the memory. This is also good because if stack canaries were used on this particular network service, we would be able to bypass them even if that mitigation was in effect. Now, the first exploit I wrote, I was sort of just assuming that ASLR wasn't turned on. We'll eliminate that caveat shortly, but let's make some progress. libc in this particular network service doesn't include any null bytes. It's in the high address space. So we can write our exploit using ROP. We don't have any null bytes in our ROP chain, and our exploit works, and we're able to get code execution. It's not very good, though. We need to, real devices are going to have ASLR turned on, so we need to be able to bypass that for this exploit to be useful. I audited the web server in more detail, and I found that if I put a carriage return as part of a HTTP header, the web server will actually search for that carriage return and replace it with the null byte as part of its processing of text strings. And so we can actually get null bytes into our ROP chain now by putting appropriate use of carriage returns into our shellcode, basically, or our ROP chain. So that's pretty good. We can get pi addresses into our exploit, and this is a pretty good position because pi, we can get pointers to sort of the application code and data for a non-pi binary. There are fixed addresses that include null bytes. And we can't use our gadget anymore, like our traditional gadget, to move the stack pointer into the first argument because we're using that vtable function pointer. We're not using sort of that classic thing anymore. But what we can do is there's a register pointing to attacker-controlled data, and we can pivot our argument register and return into system in our binary, bypassing ASLR because we're using fixed addresses for code and data in our non-pi binary. We're able to put arbitrary payloads for our system library call and execute shell commands. We can start a telnet service and running on a high port with the login as binsh and get a root shell. So we've finally got a 100% reliable exploit. This particular this particular device doesn't actually have telnetd on the file system. Most embedded devices do have telnetd available to them. It's just a default way that this build environment works for when embedded devices are built. But this particular device doesn't have telnet present, but we're just going to create a file ourselves by echoing escape characters, hexadecimal characters, writing a binary that creates a bind shell, and then we can telnet to it. This exploit is 100% reliable and would also work if stack canaries were used, since it doesn't overwrite the return address. So it's a very useful exploit now for this particular target. And that's pretty much the end of that 0-day. But let's look at a router in one last vendor. It's a different vendor, DLink. And this router, it's just a video. I'm not going through the exploit itself. But I went to my local consumer electronics store, and I said, I'll buy the most expensive router that they have available to me, and I'll buy that, and I'll take it home, and I'll see if I can find a 0-day and write an exploit for it. And when I took it home, I sort of looked on the internet, and this device was actually end of life. Maybe that says badly for my electronics store that I was using, but this device was end of life. And for a lot of these vendors, end of life means that there will never be any more patches against these devices again. They'll never do any security fixes. And if you have any bugs or 0-days in these devices, they'll be ever present so long as there are devices still on the internet. And this is, as you get more expensive, they start to look like spaceships, these routers. This is connected over a network cable, but Wi-Fi is equally applicable. I'm setting a Netcat listener on port 4444, and the idea is that the router is going to be exploited and telnet back into me with the connect shell. It's a multi-staged exploit. I'm sort of building the payload as I go, so it takes a little bit longer than single web request or anything like that. But it's building the exploit, and it's completed. When I go to my other terminal, and I should have a shell now, I run uname -a, and it's running an ancient kernel. I'm running as root on the device, and I'm on the root file system. Again, this is a really sort of common problem with IT devices and embedded devices, is that management of their security life cycle is pretty bad, and once these devices become end of life, and there's tons out there, what happens to them? They're just sitting out there on the internet waiting for exploitation, I suppose. So that's pretty much the end of my talk. IoT 0-day engineering does take some work. There are approaches you can use, processes and methodologies that make it easier. It is achievable, and it is an important part if you want to sort of see if you can find a 0-day and write an exploit for some of these devices like you have at Pwn to Own. We actually do training at InfoSec, and these are a bunch of routers that we store for that training. But thank you very much. I hope you enjoyed my talk. It's great to be in Argentina, and if there's any questions, I'm happy to take them.